Hello, everybody. Miss Peachy from your WCA physics class. So I've decided to make some videos to kind of help you out a little bit with these concepts. I've been noticing that some of you all are struggling with them, and I just wanted to make sure that you have a clear understanding of what you're doing so that you're basically doing as well as you can. So I'm going to walk you through the first lesson I'm going to walk you through is the accuracy and precision lesson because I felt like that was kind of a tricky lesson. And then if after taking, this lesson here, if you decide that you would like a redo on this quiz, just let me know and I can reset that for you. So remember, you get to reset them if you didn't do well on them. So I have the quiz up on, or the lesson up on one side, right there, and a whiteboard up in front of me that I'm going to use to write on as well. So accuracy and precision and significant digits and uncertainty are basically the concepts that are covered in this lesson, and they're kind of tricky. So the idea behind accuracy and precision is basically that when you're in an investigation, a laboratory setting, in physics, you're doing a lot of, you do some controlled laboratory settings with like simulations, and you also do stuff in the field, real life kind of physics settings, physical world settings where you're taking data as well. But as you're taking data, that there's going to be a range of data that you get. And it's not going to always be the exact same number. And so you have to decide, or you have to look at that and analyze it and see if it's precise, is it accurate, or is it both? And I really think that the best explanation for me, anyways, is the visual one. I like the dartboard explanation because it helps me visually understand better. So the idea is that accuracy is to get as close to the expected value as you can, right? So if the expected value is to shoot a bullseye, then getting as close to the bullseye as possible is pretty accurate. So if I'm throwing darts and I do this, which guess what? I do that all the time. I'm like right there, one dot away from the bullseye. I'm pretty accurate. I'm not accurate enough, unfortunately, but I'm pretty accurate. I'm getting close to the bullseye, but I am not precise, and that's my problem actually. In real life, in darts, I'm not precise. They're all over the place, but they're really close to that bullseye. Precision is where I take a data measure, and every time I take a data measure, I'm really close to the data measure I had on the previous time, right? It's not necessarily accurate, but I'm very consistent with the measurements. So this clustering of darts is very, very precise, but it's not at all accurate because my goal is that giant bullseye. What's up with that? My bullseyes are way smaller than that. I'd be much more accurate if I could have a giant bullseye, but I digress. This is very precise, but not accurate. If I could, in my dreams, shoot like this, it would be both accurate and precise. I would actually be able to hit the bullseye all the time because I'm hitting my target. That's the accuracy part of it. And I'm consistently hitting the same spot each time, which is the precision part of it, right? So that might be review for you because we talk about that in physical science. And so that's something you may have seen before. Now, uncertainty is something you maybe haven't seen before. And so the idea behind uncertainty is that there's always some degree of imprecision in your measurements, right? So there's a little bit of guesswork that goes on, and you don't know, that guesswork is usually represented in the last digit that you're measuring with. So, for example, if I have a ruler, a metric ruler, right, and you have your here's 0. Here's my 1 centimeter mark. And you have 10 millimeters in between. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is at that 1. If I'm measuring something next to this, and I want to measure the length of that green bar, I can measure how many millimeters this is. I can say it's 1, 2, 3, 4, 5 whole millimeters. And then this part here, come on, don't do that. I don't want to do that. I'm just trying to draw a line, is a guess. It's an estimation. I'm going to estimate that at 0.9. This represents a degree of kind of an estimation. So that's the precision of this particular measurement is to the tenths place. Let's say instead of having 10 marks in between, I was able to have it where there were those 10, I shouldn't have erased the 10 marks, but I'm going to do it anyway. 1, 2, 3. And then in my world, I'm going to make this bigger, okay, because I can do that. I actually have a magical touch here where I can make this bigger. There are 10 more in between each one, right? I can't draw that small. I'm trying to, but this line goes so magnified. Let's see if I can do it here. I did it. Yay. Okay, so in this situation, if I want to measure this line, right, I can measure the number here, 1, 2, 3. I can measure the number here, 1. I need to actually use my pointer. 1, 2, 1, 2, 3. I'm going to try to make that a bit bigger again, just so we can see that. But I can actually measure right here, 1, 2, 3, right? So I can say it's 3.3, and then it's somewhere between the 3 and the 4. It's real close to the 4, so I'm going to call that 9, 3.39. So my 3 and my second 3, so 3.3, those were physical things that I measured. The 9 is the estimate. So I'm estimating to the hundredths place. So in that situation, my instrument is more detailed, so I can be more precise. I can be precise to the hundredths place, whereas this time I can only be precise to the tenths place. So the physical markings on the instrument that you're using are determining the level of precision that you have. And that's probably one of the more common ways in which precision is affected by using either a more precise or a less precise instrument. So precision is reflected in the number of decimal places that I'm measuring to. There should only be one estimate, and that's that last digit. So you can't estimate twice, you only get to estimate or guess once, right? So this is more precise and this is less precise. We're measuring two different lines, obviously, there. Okay. So that is what we talk about with precision. What that means, that guess, by the way, indicates the level of uncertainty. So with my first measure, I was uncertain plus or minus, a certain tenths, right? And the second one, I was uncertain to a plus or minus of the hundredths place, right? So I was more, the uncertainty was greater with the less detailed instrument. So lower precision indicates higher degree of uncertainty. Higher precision indicates a lower degree of uncertainty. All right, so when we look at the measurement that was, or the example that was given here, they talk about a bathroom scale. And on that bathroom scale, if you had, the markings were in the single digits. So we had 141, 142, 143. It's a very large scale with lots of, and the needle came to like here. Okay, what this is saying is that your weight is more than 141.5 because it's greater than the halfway mark there. It's more than 141.5, but less than 142.5. So your weight is going to be 142 plus or minus 0.5 pounds. So unless I'm misunderstanding it, say, right. So yours is close to that 142 mark. And perhaps it's not as nice as that because sometimes, those little those little needles are kind of small, so maybe you just kind of see it like here-ish. And you're just like, all right, it's somewhere between 141 and a half and 142 and a half, and I can't quite tell. So that gives us that plus or minus half pound mark, right? So we're measuring again. The smallest marking is the 1, so then we have to say that it's somewhere between the half mark. We don't know. So it's giving us that uncertainty. Okay, and it's also telling us here that one of the main reasons for uncertainty is the measuring tool limitations, which is what we kind of went through with the different rulers that I showed you a minute ago. And that applies to like all devices, graduated cylinders, scales, doesn't matter, thermometers. So then it talks about percent uncertainty. And percent uncertainty is how we can take that plus or minus 5 pounds and then convert that to a percentage. And it tells us that oftentimes, you can look at like a whole range of values and you can come up with your uncertainty and then also then apply that and come up with a percent uncertainty. So the first part is actually just calculating the uncertainty altogether. And it's using the half range method to do that. That's the method, by the way, and this is important. It's called the half range method. So to get the uncertainty, which they use this symbol to represent uncertainty. Oh, I don't like that. I can't draw it very well. And I have to do a quick, let's see, hang on a second here. I don't know what that letter, I have just a Greek letter that I don't know. And I gotta determine it because I just don't know the Greek letter. It is, no, it's, okay. So it is lowercase delta. That's what it is. All right. So it looks like an S kind of, or like a weird, it's like this. There we go. That's the denotation for uncertainty. And that is the uncertainty that's like the plus or minus 5, okay? And then, so basically this is your value right here, right? And the little lowercase delta is saying, I'm uncertain about that value to this point. And then the uppercase A is indicating the value. I sometimes don't like shorthand because it becomes a bit confusing. So this is your uncertainty, and this is your expected value right here. Okay. So in the case of, first of all, we got to find the uncertainty. So to find the uncertainty, we use the half range method. And basically you take the range and divide it by 2 because it's half range method. So for this, our range is the high minus the low. So we have 2.3 minus 1.7. That's our range, which is 0.6 apparently. And we take half of that, we divide it by 2, which gives us 0.3 as our delta A. Okay, and then the expected value is 2. So the side story here is I'm buying shrimp because it's delicious, and I want 2 pounds of shrimp, and sometimes they're giving me 2 pounds of shrimp, and sometimes they're giving me 1.7 pounds of shrimp, and sometimes they're giving me 2.3 pounds of shrimp, but they're always charging me for 2 pounds of shrimp. So sometimes I'm making out like a bandit and getting almost an extra half pound of shrimp, and sometimes I'm getting shortchanged, but in average, it's pretty much 2 pounds. So what the uncertainty is you take, and then you multiply this by 100. So 0.3 is that half range value of the uncertainty. And 2 is the expected value. And then multiply by 100, and that gives me, I think it's 15%. So the uncertainty is 15%, or it's 2 plus or minus 15%, right? So I'm getting either 15% more or 15% less, somewhere in that range. Depends. It's right around 2, but that's my uncertainty. So that's how you do that. That's how you use a half range method to determine the uncertainty and then take that uncertainty and divide it by the expected value times 100 to get the percent uncertainty. All right, and then the next slide is talking about what would happen if I had to calculate things and I had two measurements that both were uncertain. So we do a lot of calculations in physics, and you're going to be getting to that starting next week. So one of the earlier calculations you'll be doing is for speed. So speed is distance divided by time, right? Well, what if my distance is 10 meters plus or minus 2, and my time was 2 seconds plus or minus 1? Then what it's telling you here is if you're multiplying or dividing, it doesn't matter. You go ahead and do this part first, so that's 5 meters per second. And then you have to add your uncertainties together. So 2 plus 1 gives us a new uncertainty of plus or minus 3. So you're adding those two together. Okay, that gives you the combined uncertainty because the uncertainty of any two values that are multiplied or divided is greater than the uncertainty of either one alone. Okay. And then we get to significant figures here. Erasing. So significant figures are telling you, again, that degree of precision of your instruments, right? So when I report something to a certain level of significant digits, I'm essentially stating that I've measured and confirmed that that is 100% true. So if we went back to my measuring tool, and I had 0 was there, so 1 is here, 2. So if I have, I don't think I did that very good. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, there are 10 markings in between, right? So if I put something up against here and measure, remember you're allowed one estimation. I can report this measurement as being 1.123. Those are measured and confirmed. And my estimation, I'm going to put a 3. This is my estimated value, right? So there are 3 significant digits here. That indicates that I have measured to that degree of precision. If I recorded it as 1.331 or 1.332 or something like that, then I would be a liar. I would be a liar because I did not look at, I have no way to confirm that that's a 1 there. None. So you can't do that. You have to use the instrument provided to measure to the correct degree of precision. And when you are calculating stuff too, the answer in the calculation has to also reflect the degree of precision that's presented in the measurements that you're given. So we'll talk about what is significant, what is not significant, and how you can figure that out based on your calculations. Okay, so significant digits are any digit that is, well, okay. So it's giving a special case to zeros because zeros can be a little tricky with significant digits. So zeros are only considered to be significant if they don't reflect just an indicator of place value. So when you're doing a decimal, the leading zeros do not count as significant digits unless they're preceded by a number that's non-zero. So this has one significant digit, and that significant digit is 3. These leading zeros are just placeholders, so they're non-significant. If I were to write, now this zero is significant because it is preceded by, it's on the left side of it, there is a non-zero number. So that tells me that I must have measured that there was nothing in the hundredths place. So it can be a little tricky, I'm not going to lie, because sometimes there's nothing and you did measure. And there's nothing in the you know, tenths or the hundredths place, and you still measured it, but technically they would not be considered significant digits. I don't know. It's kind of tricky in that way, but this is the rules that we're following here, right? So the trickiest part is if you have trailing zeros in a whole number, they give 6,700 an example, it's hard to tell if these are significant or not, because did you really measure and there was nothing there, or did you just estimate? You can't really tell. So to get around that and the other one, if you use scientific notation, that kind of like circumvents the issue. So if I write down 6.7 times 10 to the third, then I have two significant digits. If I were to say, I really did measure these, then I would write it down as 6.700 times 10 to the third, because then that tells me that all of those are significant. So you can write it that way if you're trying to reflect that, yeah, in fact, I did count exactly to the ones place and there was only 6,700, I promise. So then you would want to write it in scientific notation to indicate that, yes, those are significant. Then when we're multiplying and dividing significant digits, it's a bit tricky. Well, it's really not that tricky, but it's kind of confusing because I think the language is a little different. Because we're talking about significant digits and then precision, and they're not the same. So when you have high precision, remember, that means you would have a higher number of significant digits. And if you have low precision, generally you have a low amount of significant digits. If you have high precision, usually that means you have more numbers or more decimal points too, right? So more numbers to the right of the decimal, but they're not exclusive to each other. So for multiplication and division, you are going to use significant digits. You pick the number in the problem that has the lowest number of significant digits, and that's what you report your answer to. So in this example, 1.2 has the lowest number of significant digits of 2. So my answer is reported to 2 significant digits. Okay? Significant, not necessarily to the tenths place, to 2 significant digits. If my answer had been 45, I would not have reported 45.0. I would have reported 45 because that's 2 significant digits. So with multiplication and division, don't pay attention to the decimal place. Pay attention to the number of significant digits. With addition and subtraction, pay attention to the decimal place. That's the difference. So the least precise of my number, 16.7, is to the tenths place. So my answer also then must be to the tenths place. It doesn't matter how many significant digits it has, it matters the decimal place that you're reporting it to. So in this case, they both have 3 significant digits, but that's just coincidental. It's the number of the decimal place. It's to the tenths for both. And then the final one, significant figures in uncertainties. I want you to just put a pause on this slide at the moment because I am trying to get clarification on the slide. I don't think this makes sense the way it is written. The way it is written, it says uncertainties should have the same level of precision as the measurements, right? Precision is the number of decimals to the right of the decimal place. So our measurement here is 2.50, which gives us 2 digits to the right of the decimal. That's the precision, 2.50. If we follow the rules, then the precision or the uncertainty should be 2.06, which it is. We have 2 decimals of precision, or yes, and 2 decimals of precision. They didn't give us that. They give us 2.5 instead of 2.50. I don't know why they changed this here to that. Doesn't make sense. I think it's a mistake, but I'm getting clarification on it from Connexus. The other thing is that the quiz is also then mistake. The quiz is written, as far as I'm concerned, incorrectly. So at this point, I'm going to go back and I'm going to award 100% correct for everybody on that question on the quick check, because I don't think it's worded correctly. I don't think it's written very clear in the lesson. I'm hopefully going to get that changed or clarified for me going forward. But for the time being, this is one of the questions on the test has to do with significant figures and uncertainties. And if you got it right, good for you. And if you got it wrong, you're still going to get it right. I'm going to go back and fix that for everybody involved. So that's everything in the lesson. There's just some practice problems and stuff like that. If you have any questions or concerns, let me know. I'm going to try going forward to be doing these for the lessons as well, so that you guys can have some sort of explanation as you're going through, and hopefully you're finding this helpful. If you find it helpful, can you email me and let me know, because that would be great. It would allow me to know that doing this is actually worth my time to do it because it's helpful to you. And that is always what I strive to be, is helpful to you guys. So have a great day. Let me know if you have questions or concerns, and let me know if this was useful.